Hi everyone, so I'm going to be talking about Chapter 5, which is on one-way analysis of variance or single-factor analysis of variance. And this is putting together the abstract information that we talked about in Chapter 3 about the treatment index with the more concrete numeric calculations of the F statistic that we talked about in Chapter 4. Okay. So it's a little bit of a long chapter because it's blending two types of information together. But hopefully everything will feel a lot more clear by the time we're done with this chapter. So in this video, I'm going to be talking about the sampling distribution of F, which is looking at what kind of values of the F statistic can you get when the null hypothesis is true. Okay. And we'll talk about how we use that sampling distribution to get us a critical value for F, which we use in our decision rule, and how we use that decision rule to help us make decisions about which hypothesis is supported and how to write our conclusions. Okay. In future videos on Chapter 5, I'll be talking about what are the assumptions underlying analysis of variance. This is about what kinds of characteristics your data should have in order to be confident in the results you get with analysis of variance, and how to correct for one assumption that's frequently violated. And so this is the correction for unequal variances. And then I'll also do another full example of analysis of variance from beginning to end. So hopefully that'll help you put everything together. And lastly, I'll talk about independent samples t-test, which is a mathematical equivalent to single-factor ANOVA when you only have two groups. Okay, so we have a lot to cover, but I hope that by the time we're done, you'll be a lot more clear about what exactly goes on in the F test, the analysis of variance. And it's really going to lay the foundation for all of the different types of hypothesis testing we're going to do this semester. Okay, so before we get into the sampling distribution of F, I want to remind you a little bit about what we've been talking about with the treatment index, which is our F statistic. All right, a little sloppy. Okay, so just to remind you, so our F is our treatment index, and we calculated that by doing our mean square A divided by mean square S over A. Okay, mean square A is our between group variability. Okay. And just a reminder, between group variability is looking at differences among our group means. And so it's really picking up on variability that's caused by our treatment effect, but it also picks up on variability caused by chance factors or experimental error. Mean square S over A is our measure of within group variability. And it is just a measure of chance factors or experimental error, because it's just looking at how people's scores within a single group that everyone received the same treatment, but yet they don't have identical scores. So it's looking at that variability. Okay. And also to remind you, if F is close to 1, that supports the null hypothesis and this idea that there's no treatment effect present. On the other hand, if F is greater than 1, that tends to support the alternative hypothesis that there is a treatment effect present. Okay, that being said, we've talked about this fact that, well, how much bigger than 1 does it have to be before we're confident that we have a treatment effect present? Well, to help us make that determination, we use the sampling distribution of F. And so I'm going to draw a little graph here. Okay, so this is our graph. So you can see along the x-axis, we have potential values of the F statistic when our null hypothesis is true, okay? And along the y-axis, we have frequency, okay? And so this is what the sampling distribution of F looks like, although I'm not the best artist in the world. So what you see is that because this is when the null hypothesis is true, when the null hypothesis is true, F should be around 1, okay? And you can see I have a little line here for 1, that most of the values of F when the null hypothesis is true is around 1, okay? The peak of this graph, okay? However, sometimes you're going to get values less than 1, and you can see this tail going off here into infinity. Okay, that tail is showing that on very rare occasions you can get values quite a bit larger than 1, okay? Even when the null hypothesis is true, even when there's no treatment effect. And so we use this sampling distribution of F to help us decide how big our F needs to be before we are confident that we should reject the null hypothesis and conclude that our independent variable is having an effect on our dependent variable. And so we look at this sampling distribution of F and determine, okay, what level of risk we want to have. And usually in social sciences, we choose a level of risk at approximately 5%, sometimes 1%. And then we would look at the area under this curve, and we find out, okay, here's a line where this area alpha equals 0.05. And on this side, on the left side, we have 1 minus alpha, which would be 95% of the area, okay? And so we would call the area to the right the rejection region. And if our F statistic is bigger than this line, this is where we would reject the null hypothesis. And if our F statistic is smaller than that, it falls into this region of non-rejection. So even if it's bigger than 1, even if it's quite a bit bigger than 1, if it's still on the left-hand side, we can't be 95% confident that the results are consistent with a treatment effect. It's still possible you could get that value when the null hypothesis is true. And so we would say over here that we're going to fail to reject the null hypothesis. Okay, and so what is this number? It's going to depend from question to question. In our particular example with our F statistic, I'm going to just draw down here, it would be 4.26. We call this F alpha, or our critical value. Okay, and so if our F value from our data is larger than 4.26, then it's going to fall in this rejection region, and we would reject the null hypothesis. And the reason for that is because it's very unlikely, less than 5%, that we would get an F value that big when there's no treatment effect present, when the null hypothesis is true. Okay. On the other hand, if we get our F statistic and it's less than 4.26, then we're going to fail to reject the null hypothesis, because even though it might still be larger than 1, there's still a reasonable level of probability that we could get that value when there's no treatment effect present. Okay, and so we say we don't have enough evidence yet to reject the null hypothesis, so we would fail to reject the null hypothesis. Okay, so if we think back to what we did in Chapter 4 when we calculated our F value was actually 13.64. So our F value is actually way out here. 13.64 would be our F obtained from our data. And so that's clearly larger than 4.26. So in that situation, we would decide to reject the null hypothesis, because getting an F value of 13.64 is extremely unlikely when there's no treatment effect present. So instead, it's actually very likely that we do have a treatment effect, that in our example, the amount of coffee consumed did have an effect on number of hallucinations. Okay, so that's the idea of the rejection region. Okay, and so you can see I used this alpha. Okay, alpha is what we set as our criteria. Okay, so alpha is the level of risk of being wrong that we're willing to accept. Let me rephrase that a little bit. Alpha is the level of risk of being wrong when we reject H naught that we are willing to tolerate. Okay, another way of putting that is that alpha is the probability of making an error when we reject the null hypothesis. Okay, we actually choose that risk. Okay, so if we say alpha is equal to 0.05, then there's a 5% risk. Sometimes that we decide that's too much, and so maybe we'll set it to 0.01. That would be a 1% risk. Okay, but that's something we control as a researcher. We choose what level of alpha we want to use. In this class, I'll always tell you what alpha to use on your homework and also on the tests, and it'll always either be 0.05 or 0.01. Okay, but it just goes back to this idea that we're never 100% confident. There's always some risk that we're wrong. okay, even if the risk is small, 5% or 1%. And that's why we would never say that we've proved our hypothesis. We've just supported it, and we can be very confident, but it's never 100%. Okay? All right, so now I want to talk about, this was the general idea of the sampling distribution of F, and sort of how we get to our critical value. Now, statisticians have created statistical tables to tell us these values, like the 4.26, to use in our decision rules, and it's based on the idea of what you would expect when the null hypothesis is true, but it's also based on characteristics in our data. Okay, so using the F table to get our F alpha, or critical value. Okay. And so to do this, you want to use the table in your book. So it's table A2, and it starts on page 530 in Appendix A of your book. I'm going to show you the table in a second, but before we get to that, you need to know certain information about your example in order to do this. Okay, so you need to know your degrees of freedom, for between group. This is your degrees of freedom for A. Okay. You also need to know your degrees of freedom for within group. Which is your degrees of freedom for S over A. Okay. And lastly, you need to know your significance level, which is alpha. Okay. Okay, so for the example I did for you in Chapter 4 with our amount of coffee, our degrees of freedom for A was equal to 2, and our degrees of freedom for S over A was equal to 9. Okay, and then we're going to use alpha equal to 0.05. Okay, so we're going to look up in the table here in a second to find out what our F alpha should be in that circumstance. Okay, so I'm going to switch to the table here. Okay, so this is the table you want to use. You can see it says table A2, critical values of the F distribution. Now, where it says degrees of freedom for the numerator, that is your degrees of freedom for A. Okay, and where it says degrees of freedom for denominator, that is your degrees of freedom for S over A. Okay, and so the other thing you want to know is this part here where it says boldface type are critical values of F at alpha equals 0.05, and the numbers listed in light type, okay, are for F with alpha equal to 0.01, okay? So we're going to look up so we want to look at the second column, okay, and then 9. So it's not even on this page. We have to go, oops, we have to go to the next page. So we're going to look at 2 and 9. And those are our critical values. So 4.26 would be the critical value if alpha is equal to 0.05, and the light phase one, 8.02 would be for alpha equals 0.01. Whoops, 0.01. Okay, so we're going to use 4.26. Okay, and this table actually continues on for another page. So it's on 3 different pages in your book. Okay, so I'm going to go ahead and close this. So remember, we want to use 4.26, which is the number I actually wrote already. Okay. All right, so it's 4.26. Okay. All right, and so that's how you look up your critical value in the statistical tables. So you use your alpha that's given in the problem, your degrees of freedom for A, and your degrees of freedom for S over A. Now, that F alpha, that 4.26, is going to go into our decision rule. Okay, so we're going to go back to this idea of decision rules. And so we're going to write if the obtained value of F, okay, equals or exceeds our critical value F alpha of 4.26, we're going to reject the null hypothesis otherwise fail to reject the null hypothesis. Okay, so you're going to write this decision rule this way every time, pretty much, except that the number in the blank is going to change depending on what your degrees of freedom are and what your alpha is in the problem. Okay, so just a reminder, this obtained value of F, this is your F from your data when you calculated the F statistic. So for us, it's that 13.64. Okay. We're going to compare that with our critical value, or F alpha, of 4.26. We're going to use this rule to help us make our decision. Okay, so in this case, our decision should be to reject the null hypothesis, and that is because our critical value of 13.64 is bigger than our critical value of 4.26. Okay, so that, because if you look at our rule, it says that if our F value, which is 13.64, equals or exceeds 4.26, their critical value, we're going to reject the null hypothesis. So that's what happened. Our 13.64 is definitely bigger than 4.26, so we're going to reject the null hypothesis. Then we're going to write our conclusion. Okay, when you write your conclusion, you're putting this information back in the context of your independent and dependent variable. Okay, so amount of coffee consumed had a significant effect on number of hallucinations. Then we're going to give some statistical information. We did an F test. Our degrees of freedom were 2 and 9. And our F value from our data was 13.64. And then we have P less than 0.05. Okay, so this is a lot of information in this conclusion. So let me just break it down for you, because you're going to need to put it in the context of your homework problems and your test problems. Okay, so first of all, amount of coffee consumed. This is our independent variable. Okay, number of hallucinations. This is our dependent variable. Okay, so you want to say, if you reject the null hypothesis, you want to say your independent variable had a significant effect on your dependent variable, but put it in the actual context of what your variables are in that problem. Now, significant is an important code word in statistics. When somebody says they had a significant effect, it means you rejected the null hypothesis. Okay? So it's important to include that word. That is a word that everybody familiar with statistics knows that if that word is included, it means the null hypothesis was rejected. If it's not included, then it's ambiguous. Did they reject it or did they not reject it? Okay, so it's important to include it if you rejected the null hypothesis. All right, then we have the statistical information down here. So the 2 is your degrees of freedom for A. The 9 is your degrees of freedom for S over A. The 13.64 is your F from your data. Okay, a lot of students get this mixed up and they would put 4.26 here. They would put their critical value here. You do not want to put F alpha here. You want to put the F value that you actually calculated on, from your data. Okay. Now, the p-value, this is has to do with alpha, right? You can see the 0.05, that is our alpha value. When p is less than like this, you write it, p is less than when you reject the null hypothesis. This means the probability that you're wrong in rejecting the null hypothesis is less than 5%, is very small. Okay, so let me write that down here. So this is the probability you are wrong if you reject the null hypothesis. Okay, so in our case, 13.64 was a lot bigger than our critical value of 4.26. So it's very unlikely that we would be wrong in rejecting the null hypothesis. So that is why we're saying the probability is less than our alpha of 0.05. Okay? All right, so let's talk about what happens if your F value is not larger than your critical value, okay? So what if our F was equal to 3.64 instead of 13.64? Okay, so if it was 3.64, well, we look at our decision rule. Here's our decision rule. If the obtained value of F equals or exceeds F alpha of 4.26, we reject the null hypothesis. But 3.64 is less than 4.26, so it falls into the otherwise part, and so we would fail to reject the null hypothesis. Okay, so then our decision would be to fail to reject the null hypothesis, okay? Because even though this F value is bigger than 1, and there's still some support for the idea that we have a treatment effect, it's not reaching that level of significance, okay? So this is because 3.64 is less than our critical value of 4.26, okay? So in this situation, then our conclusion would be the amount of coffee consumed did not have a significant effect on number of hallucinations. Okay, and then we would have F with, F with 2 and 9 degrees of freedom, but now our F is only 3.64, right? That's what we're pretending, right? And so in this situation, our P is greater than 0.05, okay? So again, we still have amount of coffee consumed, so still our IV, but now we're saying it did not have a significant effect, okay? Did not have a significant effect. And on our dependent variable, okay? We still give our degrees of freedom for A. We still give our degrees of freedom for S over A. And we still give our F from our data. Okay. Again, remember, P is the probability we would be wrong if we reject the null hypothesis, okay? So the probability we would be wrong if we reject the null hypothesis is greater than 5%. It's greater than our alpha, okay? Because of that, that is the whole reason why we failed to reject it. The probability we would be wrong if we rejected it is larger than our alpha, so we don't want to reject the null hypothesis here. The risk is too high that we would be wrong. It's greater than our alpha of 0.05, and so we're not going to reject the null hypothesis. Okay, so that's how you would write your decision and conclusion if you fail to reject the null hypothesis. If your F value from your data is smaller than your critical value. Okay, I want to talk about one last thing before I end here, which is, what if you have two groups and you reject the null hypothesis? Okay, so if you have only two groups and you reject the null hypothesis, you write your conclusion a little bit different. Okay, you want to write a specific conclusion comparing the two groups. Okay, so let's say in our experiment we only had 8 cups and we only had 0 cups. So what if it's only 8 cups and 0 cups only? Okay, what you do is you look at the group means. So already we're saying our decision, we know, is going to be reject the null hypothesis. Okay, so we're going to say, let's say it's still 13.64, so that's bigger than our critical value, 4.26. Okay, but now we only have 2 groups in this example. Okay, and what you do is you look at the group means, and you compare. Okay, and I don't remember the exact numbers, but I'm sure the 8-cup group has a higher mean than the 0-cup group. Okay, and so you're going to talk about that. So in your conclusion, you want to say that people who drank 8 cups of coffee had significantly more hallucinations than people who drank no coffee. And then you'd still give your, same F information. Okay, so that part stays the same. The main thing that changes is that when you only have 2 groups, you want to talk about how the 2 groups, 8 cups, 0 cups, no coffee, you want to mention both of them and say which one had significantly more or significantly less than the other. Okay, so you want to be more specific when there's 2 groups. You only have to do this if you reject the null hypothesis, right? The only reason you have to do this when you reject the null hypothesis is because you only have 2 groups and they're different, right? So when you have 3 or more groups, if you remember, the alternative hypothesis is that not all the mu's are equal, but it doesn't say which one's different, which ones are different. We're going to talk about that in chapter 6. How do you tell which groups are different? So when you have 3 or more groups, you write a vague conclusion the independent variable is having a significant effect on the dependent variable, okay? Because you don't know which groups are different from each other based on the F statistic, okay? However, when you have only two groups, you know they're different if you reject the null hypothesis. And so you want to talk about how they're different in your conclusion, all right? Okay, so that then is information on how to find your critical value and write your decision rule using that critical value, that F alpha. Then how to compare your F statistic that you calculated from your data with that decision rule to make your decision. And I showed you the different ways to write your conclusion depending on how many groups you have and whether or not you reject the null hypothesis. Okay, so remember, I will be doing another example later in another video. So if it's still feeling a little confusing, don't worry yet. I will go through this all one more time. Okay, all right, so that's the end of this video.